Well, I'm delighted to be here and thank you all for coming. Here's my talk. I'm going to talk to you about stress percolation and shear localization. And I think my first slide, do I have a slide? There we go, acknowledgements. This project is not actually one of the ones that I mentioned. I'll view it.
Thank you.
Okay.
I wasn't gonna say.
But it's kind of a little side project, so I have to acknowledge that people always fund me when I'm doing side projects. So anyway, thank you for the funding. I would say this is my pet project. And it's a pet project because it's a really big project. I like to think of this, and I don't know, do we want to drop the lights bit? Can you do that?
I'll
Is that-
try this.
Okay, just maybe a little bit. Yeah, that's better. Okay, I like to think of this as I'm playing the long game here. I'm interested in this question of how do polycrystals work, and I'd like for us all to think about perhaps some almost a paradigm change in the way we think about polycrystalline materials, because well, they're very, very complicated. So just quickly, this is a I love this. Thank you. This is a tracing of a thin section of just some random granite. Okay, so you look at the grains in the granite. I haven't identified who's feldspar or who's quartz or mica or whatever, but we just have a bunch of really messy looking stuff. I mean, if you look at rock, it's really, really complicated, and we want to squeeze this and describe its behavior with a nice scalar. We say, oh, this is the flow strength. This is the bulk modulus, right? There's something simple out of something horribly complicated. And so I want to start by just reminding us about some of those simple scalars and then how they might become more complicated. So just elasticity, just so we're all on the same page. Elasticity, for example, Young's modulus here is the spring constants of a rock, right? So the stress is equal to the Young's constant times the elastic strain, and the elasticity, the elastic strain is defined in this direction as x over x, right? And this for rocks it tends to be extremely small, and so a lot of people in rock deformation ignore elasticity. I think it's completely irrelevant. Now, of course, I know we have some seismologists here, and elasticity is your game, right? So it's very important. But in the community that I tend to live in, we tend to look through elasticity because it's very, very small. It doesn't give you very much deformation. So the Young's modulus here is defined as where is it? Lost it on the page. Yeah, so here's the Young's modulus, which is the spring constant. It's defined in this direction. Then we have the Poisson's ratio. It's another nice scalar, which is how much the rock kind of poops out sideways, right? When you push on it this way. So delta y over y divided by delta x over x. Okay, so that's a nice scalar that we can think about. But in reality, when we think about our rock, if we don't think about it as a black box and it's full of just black box stuff, full of crystals. Crystals have crystal lattice, they have different symmetry. And so this introduces a lot of complexity. So here is the way we describe the elasticity of single crystals. So we stress rather more properly as a tensor, right? Second rank tensor, strain is a second rank tensor. And so they're related to each other by a fourth rank tensor, which is like this 40 box at 81 numbers. But fortunately, mercifully, due to a lot of symmetry and the nature of things, as well as crystals, that box of 81 numbers that define the full elastic behavior of the material can be reduced to a box like this, right? We call these, the CIJs, right? The elastic tensors, but the elastic single crystal elastic constant. But looking at this, it's like, how do you intuitively make any sense of that? So what I've done is just to illustrate to you the important part is that if you have a hexagonal crystal and you squeeze on it in one direction, it's not just going to like get shorter and maybe poop out. It's going to do something like that, right? It's going to strain in an unexpected and slightly weird way from an intuitive point of view. So single crystal elasticity is a lot of fun. And it's complicated, and that adds to the complexity of our polycrystal. And oh, here's another illustration of what this means. So it means the elastic properties are orientation dependent, right? So here's a plot of the effective Young's modulus. That means like I'm squeezing this way. What's the effective Young's modulus is a function of the orientation. So this is for muscovite. This is the c-axis, 001, and here's 100, the a-axis. And so what you're seeing here is that the Young's modulus, if you were squeezing parallel to the planes in the mica, right? That's where all of the silicate tetrahedra are making this little planar feature. That's quite stiff. We have an effective Young's modulus of 100. But if we're squeezing perpendicular to the planes along the c-axis, we have an effective Young's modulus of no, that's 100. That's not 100. This writing is too small here. It's 180, right? The effective Young's modulus of less than 60, right? So the mica's elastic behavior is massively orientation dependent. Similar for the Young's modulus of micropine, right? So squeezing along the primary axis, the axes, it's fairly stiff, between 120 GPa. And then if we're down here at 45 degrees, it's close to 40 GPa. So that's kind of fun and unexpected, but I just wanted to think, okay, now go back to our polycrystal. So here's our polycrystal, and I was talking about how we want to get like some scalar value out of its behavior. And then we think about it in this context. So now I've plotted kind of those effective Young's moduli on each grain, kind of different colors for different minerals. And I think this really illustrates how really complicated this problem is, right? So now imagine we're stressing the box, we're squeezing this. Each grain wants to respond to the stress that it receives in its own way, and quite different from its neighbors, right? So this grain is very stiff and sort of homogeneous. This one is, kind of weak. This one is oriented in a more strong direction. So how does that work, right? How do we make sense of this? And more importantly, how does the rock function, right? We're going to squeeze this and we want the rock to apply some pressure and that it won't turn to a pile of sand, right? But then how does it work out? Who wins and who loses in the battle of how each one of them is going to perform? And this problem is called in the material science world the polycrystalline problem. And when I first started working on this, and I was talking to somebody who was at, I think, one of the national labs, I'm working on the polycrystalline problem. And they said, you can't, it's impossible. Don't do that. Nobody works on that. It's like, you'll never publish, right? Because it's just too thorny. So what we do, for sanity's sake, is we employ a bunch of simplifications. So the traditional ones, thinking about the, I said Taylor Sack, I mean, one of these belongs down here. But anyway, just thinking about elasticity, you have the Royce assumption, which all the stresses are the same. We have the Roy assumption, which is that all the strains are compatible. It's another way of thinking your way through this problem. And then we know that both of these are wrong. So the right thing is to average them, right? So two wrongs don't make a right, but if you take the average, you're fine, right? And then more sophisticated are self-consistent schemes, which is essentially you consider each grain kind of as a little ellipse and a homogeneous elastic matrix, and you work out using the sort of formulation for inclusions in elastic. It's like a hole in the plate kind of problem. You work out what each grain should be doing, and this is far more sophisticated than these. And most of my work actually I'm doing in the synchrotron. We're using X-rays to look through the crystals and inquire, what are you doing? And what we find is that we have to use a self-consistent scheme to describe the elasticity of our material. But all of these simplifications ignore neighbor-to-neighbor interactions. So there's another way to think. This, like the other paradigm, is something called horse canes. Or you could call it stress percolation, because it's in fact a percolation problem. So what you're looking at here is from this guy at Bob Berenger at Duke University, who recently passed away. brilliant fellow. And what he did was he had these bead packs of photoelastic beads. So what you see here are these little circles. Some of them are lit up and some of them are not. The photoelastic beads light up when they're stressed. And then so you put, and what you do is you put a polarizer in front and in back. So they're not really lighting up, they're just being birefringent. Okay. So this birefringent material, and these beads are just like beads dropped in, so they have no traction. You can't impose tractions on their surfaces, they just slip. Okay. So what happens is the stress moves through in these force chains, right? These sort of semi-linear, more or less parallel to compression arrangements of grains that are bearing the load, while other grains are doing absolutely nothing. You can see here, there are a bunch of grains, they're not lit up. They may be, their experience of being loaded is just like oblivion. They don't know that they're being loaded, where their neighbors are carrying the whole load. And this arises because the only way to move force from one bead to the other, the stress or the load, is perpendicular to the contact. So if the force arrives at a grain, the only way force can be transmitted is along the radial direction. So when I first learned about this, I thought, oh, I wonder if that paradigm could be instead applied to a polycrystalline material. So I made myself a play toy. So here's my play toy. And it's a finite element model. This is a 2D model because then that way I can have a lot of grains. And each little grain has been meshed up, and each color represents a different set of elastic and plastic properties. So I have, in my play toy, I have 2,574 grains, and there are 48 elements per grain. They're all 6-noded 2D plane strain triangular elements, which you can kind of see down here. And there are 25 subsets, and each subset, which corresponds to the color, has a Young's modulus, a Poisson's ratio, and a von Mises yield strength. And the grain boundaries are only defined by a change of material, so they don't actually have a separate property. So I thought, okay, so let's see this very simple play toy. What happens when we load it? Oh, and I forgot. So in terms of my plastic properties, I have a description of the rheology that has an elastic portion and a purely plastic portion. And then I assigned I distributed across the subsets of grains, I distributed the Young's moduli in different ways. So I'm going to show you 4 models, one where I have Young's moduli going from 0 to 500, so it's like huge range, unrealistic in terms of the highest Young's modulus. And then I have them kind of clumped with a bunch of 0. Then I have another one where they're sort of more distributed, and then these two are distributed over now increasingly narrow ranges. And then usually I think all these models, I have a yield strength, which is set to, I think it's 1/100th of, it says on another slide, 1/100th of the Young's modulus. Okay, so here's my model. I load it very simply from the top, and I kind of poke it into a corner, allow it to expand out this way. One thing that's different about this from typical models of polycrystals is I don't use a wrapping boundary condition. So this boundary is just allowed to move out freely. It doesn't impact this boundary over here. And I can either put a constant load across the top or just force the top to move down a fixed displacement. Okay, so when we do that, this is what we get. This is a plot of the equivalent von Mises stress on one of my models. And when you look at this, the blue is low stress and the yellow is the highest stress. I hope some kind of pattern leaps out at you, right? Do y'all see a pattern, right? So this kind of looks like, yeah, maybe for polycrystals, we actually have some kind of percolating stress state, if you believe my model. Another interesting kind of observation here is the size of a couple of grains. And now what I'm doing is at each node, I'm just plotting the components of the stress tensor. And so in yellow now we have tension, and you can kind of see the little arrows pointing out this way. So we have regions, even though we're compressing this thing, we have regions that are slightly in tension. We have a huge variation in the compressive stress. You can see these high, the blue is the highest compression here. And again, you can pick up that pattern. And then if we zoom in a little closer, now here I've got the mesh, and I've just highlighted a grain here so you can see individual elements. So again, we can see that we have a huge variation in the level of the, this is actually, again, a tensor plot of the compressive stress on it, right? So not only do we have a huge variation in the load in this region, but we also have orientation differences. So in this region, the compression is coming this way, but in right over here, the compression is going out that way. So in this particular model, the angle in which the compressive stress, the principal compressive stress is oriented, varies through 60 degrees. So again, that's very strange because we think I have a block of material, I push on it this way, and actually, you know, within the material, the stress is going different directions, and you have, like that percolation BPAC, parts of the material that aren't seeing very much stress and parts that are seeing quite a bit. All right, so here are my 4 models. And again, I'm finding equivalent quantities of stress. And here are the histograms of the elastic moduli and how they're distributed throughout the grains. And the other thing I want to point out, first of all, you see kind of a difference in the pattern. Your eye picks up a difference in the pattern. This looks more sparse, where this looks more closely packed somehow. But the important, really big thing to notice is in this model, let's say, which has a lot of holes and this very wide distribution of the Young's models, we see an amplification of a factor of 10 in the stress locally. So this is 0.1 GPa compressive load across the top of all of them. But there are parts of this model that are seeing 1 GPa. And there are, you can ignore the negatives there. That's like numerical, tiny bit of numerical noise and other things. It's on the auto scale. But anyway, so you can see here we have a factor of 4 amplification. Here we have a factor of 3. And here we have very, very little of the stress amplification, right? So we see a modulation in the stress, but that modulation is quite small. And then over here, we have a very large modulation in the stress states within the material. And so I thought, well, okay, we know about stress chains, force chains rather, which is this little cartoon. And we know about this Royce state of stress, which might exist in a hypothetical black box material with, you know, no variation on the inside. And then perhaps we have something in the middle that are represented by my models where you have less heterogeneity and more heterogeneity, right? So that we can put this on kind of a sliding scale somehow of heterogeneity on the bottom and then various structures in the stress state. And by component, when I say component heterogeneity, I mean any structural element in the system. So I had no grain boundaries with separate properties, but you could envision, you know, I have these little hexagons, so that from a topological point of view, they're just little blobs of different stuff. So one of the hexagons could be representing grain boundaries by being very weak, and others could be representing actual grains. And so we have components, and then we have this idea of heterogeneity, and that is some measure of the variation in the statistical distribution of the elastic and plastic properties. And so that's like some knobs that we can somehow turn. Okay, so I published that in 2013, and oh, it's cut off. This paper just came out in last year, 2022, and it was, you know, we had force chains, and then we have this theoretical stuff over on the left, but colleagues of mine at Lano published this study on Brea sandstone, where they did nonlinear resonant ultrasound spectroscopy, which is basically the foot-long bar of gray sandstone, and they ping it with different excitation amplitudes, and then they noticed the resonant. They studied the wiggling of the surface basically, and the resonant frequency has a funny relationship with the amplitude, and they can't explain that unless they have, basically they can't explain it with kind of a continuum model, and they couldn't even explain it with a straight finite element model. That's what this is showing, is they have this finite difference model, which is the blue curves that they basically, they're modeling their result using the models up here. And then the red is the finite element. But the point I want to make is that in they do a micro CT, and then they mesh the whole thing, and they have their grain boundaries have properties, which is why they need the finite difference scheme. And so they put in grain boundary properties that are different than the pores and different, of course, than the quartz itself. And they get force chains in their finite element model. And the models basically explain the nonlinear resonant ultrasound. So I was very encouraged that they saw that. Okay, so the next thing I want to go on to talk about is what's going on with the plastic strength. So yeah, here the plastic yield strength is 0.01 times the Young's modulus. Okay, so here's my model, and I'm basically just now putting a constant displacement across the top. And here's the first little speck. You see a little bit of yielding here and there, a couple at the top, right? And then some more yielding, and if we displace more, we can follow it, and it develops. I think I go out to 2. It develops shear localization, right? So it just shear localizes. We don't, I mean, now I'm going to go through going up close. So I didn't tell it to shear localize. I just gave it a yield criteria. Okay, so now we're going to look up close at what happens. So here is when we first get to see some yielding. So here's a grain. You can clearly now see the hexagonal shape of this grain. And there's a little hexagon here that's yielded. So some grains that are weak happen to be somewhere in the force arrangement that they hit their yield strength. So they began to yield. And the next little bit, now you can really see the hexagonal shape grains. Unlike in the stress distribution, we see those here. And I want to focus on this group of grains here. There's 4 soft grains, and then there are 2 very hard grains with very high yield strengths right in here. So these guys have yielded. As we go to the next increment, now let me go back one. You can start, it's a little hard to see. You can start seeing these very hard grains are actually starting to yield, even though hard grains out here are not yielding. But right here, because these 2 neighbors have yielded, it forces the stress into the center, and so that grain starts to yield also. And so you can see that now we have this basically percolation of the plastic shear localization running through grains that should not shear at all, because they're, if you look at the bulk load, their yield strength is still very high compared to what you're loading from the outside. But because internally they're kind of in a pinch between 2 soft neighbors, those grains wind up yielding. And so there's this hawking, so to speak, in the material where grains that are yielding basically are casting off their load onto other ones.
Is this the same boundary condition as the other one we saw?
This
It looks like this would have a different side boundary condition.
no, this is the same model. I'm showing you a different view of it. Although what I did with some of them, I loaded to constant load across the top, and then others I had just a constant displacement in order, because sometimes I want to say, oh, across these are all loaded the same, and others I want to say I have a constant displacement so that I can keep track of the strain. So anyway, So there you can see as I go forward, it's not that these guys that were lit up before have stopped raining, but on the plot because of the way it's scaled. Right now, the strain is concentrated. The plastic strain is concentrated in these 45-degree shear beds. Okay, so that I think is the final model for that particular one. So that's okay. So here are in black and white now, all 4 models. So we can look at the variations and how the shear strain, the shear localization works. So here we have, I have different global strains on the 4 models because I have a problem with the models crashing. At some point, when you have too many parallel plastic shear bands, then the computer can't decide which one is going to do all the shearing, and so it crashes. So I have to stop at a fairly low strain with these plastic models because of the way my final model is set up. So this one, in order to get a sensible pattern and see what's going on, I have to go to 0.5% strain, whereas this one I can't get it to run at 0.5% strain. It's crashes out by the time we're close to 0.2. So this is 0.2, this is 0.5, these guys are kind of in the middle. But they're still very low strains. And you see we have shear localization and in all the models. But again, the density is different. We have a lot of shear localization here, but the amount of shear localization in the strain is small compared to up here. We have a lot of shear localization on a small number of planes, right? And then these models basically fail. They can't, I get too much shear localization, they can't go. So again, we have this difference in the patterning of shear localization, which is a function of the force structure, right? The force structure is the foundation for how it's going to shear localize. You might call this like cryptic shear localization. Like you might not, in the lab, if you produce this, you might not even notice it because I have small variations or modulations in the amount of plastic strain that are, on the order of a couple grains across, between them. And so we might not see our sample fail, where a sample like this, we might see, oh, here's a fault going all the way through. Okay, so we see this in granular materials as well, so it's not completely unexpected. Granular materials fail by, shear localization. And so this one is this paper by Hall et al. In 2010, and what they did was they used digital image correlation, and they're looking at the strain in the material. And the material is a pack, it's not a bead pack, but it's a pack of PVC pipe, right? So you go to Home Depot and you get all the different sizes of PVC pipe, and they cut them into like little, foot-long rods, and then they pile them up, and then they take pictures and they compare tiny increments in strain from picture to picture to derive the internal strain. So you'll see that this pack of granular material also fails by, shear zones. You get shear localization. This is the difference in strain, or comparing 0.4 and 1% strain. And this is a difference between an image taken at 0.4 and 1.6% strain. And this one goes out to 2.85% strain. Again, so these are just differences between the two strain steps. And so the fact that granular materials shear localize is well established. Okay, so now hopefully somewhere in your brain you're saying, but the textbook said something different, right? We've all been taught that shear localization is brittle fracture. Plasticity does not shear localize. We get rid of brittle fracture by cranking up the pressure. And right? Please tell me this is true. So it seemed really important for me to demonstrate that I can get rid of shear localization if I want to, right? And so what I can do is I can crank up the work hardening. So here's a new rheological model for my model element. So I have an elastic phase. I hit that yield stress, but then after that, I can put in a work hardening slope. And if I do that, then what happens is as I get my little shear localization, plastic shear localization, they actually fatten out. So the more I push, the fatter they get. So it's not like I have homogeneous plastic strain. I still have shear localization, but it gets really hard to, drain it enough to get shear localization through the whole model because these just get fatter and fatter, right? So they spread out. So, okay, good. Good. We're back to where we should be. We now have reproduced that plastic deformation does not shear localize. But actually, we actually see when we look up close at plastic, at ductile materials, that they do seem to shear localize. So in small ways, more of this cryptic shear localization I was talking about. So this is Padilla et al. 2012, cross-rolled zirconium under a uniaxial compression. This is again a digital image correlation type thing. They basically have this plate of this cross-rolled zirconium, which is a metal, and they spray a little pattern on the surface, and then they look at how that pattern is deforming between one image and another. And so what they see is kind of the shear localization in, so let's say cryptic kind of shear localization at 45 degrees. And the other thing that really surprised them is that they thought they were going to see a really strong correlation between the Schmidt factor, which is a measure of the propensity of a slip system to glide, right? So grains with a high Schmidt factor should deform ductily. So when they looked at this, they thought initially they would see grains, this is colored by Schmidt factor, grains with high Schmidt factors will deform and the other ones won't. But that's not what they saw. They didn't see any correlation between the local strain and the Schmidt factor. And this is a similar result, Granera et al. 2012. This is ice. And again, they have a big piece of columnar ice. They've got, the camera pointed out and they strain it, and they see the same result. So basically, they see these incipient shear bands developing at more or less 45 degrees. And the local strain within them was 10 times that of the macroscopic strain. They found locally tensile stresses or tensile strains rather within their images. And the grain strain, again, did not correlate with the Schmidt factor of the grains. Okay, so, and this is the last piece to poke at here about shear localization and how it never happens plastically is we do see sometimes these features, right? And we struggle with those, right? So that's a myelinite and some nice undeformed granite, thanks to sand atlas. Okay, so now why do we have a problem with this? So the problem is, going back to here, we have our stress, our box, and we have put a load on it. And we say to ourselves, because it's far easier to think this way, all of the stresses are in the same direction and the same magnitude as the boundary condition, right? So therefore, when something's supposed to be like ductile shear localization, when we look at this and we go, why did this part behave differently than this part out here, right? And that is because it was weaker. It had to be weaker because that's where it plastified first, right? So we have lots of people who spend their entire careers figuring out why something is weaker, right? And I would say, well, it's the wrong question. The question is not, why did that shear localize? The question is, why didn't it shear localize? Right, and it all comes down to that simplifying assumption, the Royce stress state, that we all carry around with us, maybe not you guys, but certainly me and my colleagues. We all carry that Royce state in our brains, and we know it's wrong, but it's like a paradigm we can hang on to easily, right? But here, and it works most of the time for most stuff. But there are these loose ends that we see that we can't deal with the Royce rate. We have to make these excuses for why this shear zone forms. We have to say, well, there's a shear zone there. We understand shear localization for brittle behavior, but we don't for plastic. And so we have to explain it away somehow. Okay, so the next part I want to talk about, and I think about time, right? I've got like 10 minutes, correct, or 15, something. Okay, compositional segregation and stress heterogeneity. So we know this is a beautiful garnet sitting in some sort of alternate, no, not alternate, I can't remember exactly what it's just like it's like Lucia or something, because that's what Sean works on. Sean Mulcahy gave me this photo. Anyway, so here's a garnet, and it's got this cute little beard, right? Many of you have seen these little pressure shadows, and they have a bunch of names for these things, little beard. So we know from this, just intuitively, that the disruption of the stress state around the garnet creates the opportunity for little beards to go. That's what we call them pressure shadows, is because we have that intuitive feeling that, okay, luckily things are screwed up, and now we can have a dissolution and reprecipitation or diffusion or something that can move components, the more mobile components around. And we also see segregation of phases in metamorphic rocks, but this is another huge problem we don't understand. Like, why does that happen, right? We have this a scheme that says, okay, well, you get the micas line up for some reason that we don't know. And I don't know why they line up, but they line up and then they buckle and they make little folds, and then the folds collapse, and then you create dissolution in the fold limbs, and you put things in the fold limbs. And that's the explanation for phase segregation in metamorphic rocks. But like, I always wonder, what if you don't happen to get a crenulation going? You know, that's like does it happen? You know, is that the only way? So anyway, so I thought, okay, let's try making a granite. I wanted to make a granite because my model with little hexagons wasn't very rock-like. So anyway, I made a granite, and this was an undergraduate, well, an undergraduate helped me with this. I made 6 tiles, and I matched them up, and I assigned to the grains in the tiles the elastic properties of albite quartz, case part, and like that. And then what we did was the student with his summer project was tossing dice, because I'm not very good at coding. So he tossed dice, and he took the dice would tell him what orientation the tile had and where it went. Okay, and he made this for me, my granite. And then the granite, the rheological description of the granite. So I think it's this, I forgot, I think it's Barry granite. Anyway, so I took the area fraction from just a normal granite composition, and then I used the stress that the CIJs to basically give me a suite of Young's moduli, apparent Young's moduli that would be appropriate for these minerals, and then I put in the yield strengths from the literature. Right, and so I had 34 different orientations of albite, because albite is, there's albite here. Albite is, you know, kind of highly asymmetric, or yeah. And whereas quartz is a little bit more symmetrical, not quite. Anyway, and then I couldn't have as many orientations of case part mica because I had less to work with. So anyway, so I have my model kind of set up to be granite. And I'm just going to run through these really quick. On these, I've got the compressive component of the stress tensor, and then the tensile component of the stress tensor, and here up here is the plastic strength. So I'll run through this real quick. All right, so we begin to see yielding. And then as we get yielding, that's when you can really pick up the big changes in the stress tensor. And so it does the same thing as the other models. We get shear localization, and we get a fairly strong fabric. Again, so something like forcings in the compressive direction. And also here, now I'm thinking, look at this. We also sort of have a fabric in the tensile direction, which makes sense. I mean, stress is percolating one way. It's, you know, all components have to percolate. Okay, so I have a few more. All right, so now I want to look at this. I'm going to focus in on this one, on the tensile component. Okay, so here's my tensile component. And then what I'm going to do is I'm going to blank out quartz and the mica, the things with the lower yield strength, so that the feldspars have a higher moduli. Okay, so if I get rid of them, you can see, if you sort of focus on the really bright spots, you can see that those tend to show up more in the feldspar part, okay? And, yeah, okay. So what I would say is perhaps when we get phase segregation in a rock, what it's doing is it's simply painting in the stress, the tensile stress state, right? So the more mobile components, just like in the little garnet, are able, oh, here it is. So this is like the mobile components can move around. So here is like the template in the bulk rock when we stress it, and then here would be our kind of phase segregation results. And okay, so here's the notion that, you know, in a quartz grain stuck in one of these very high compressive stress areas may dissolve or diffuse away from there, and then park itself in an area where there's more tensile stress. So it'll be just like the garnet, right? This is basically the whole material is behaving the way these little stress spheres on the garnet behave. And just to kind of back that up, I made myself a finite element model of garnet really quick. So there's a garnet in the center, and you can see the garnet makes this sort of classic disruption in the stress inside of the homogeneous schist, which is not homogeneous anyway. But if we again look at that, the pressure shadow, and we just plot those tensile stress components, component of the stress tensor, we can see the little beard right here. And the pressure shadow is about 22% of the load. Okay, that's the variation between what we see here and the ultimate load, which is the same as we see in the other models. We see that kind of variation. So it's like, if the garnet can make a beard, why can't the stress percolation make little layers? And just the last little model I'm going to show you is the idea of having soft layers and hard layers, and we're just going to squeeze them. So let's say we start making layers and that we're moving, you know, the components around in there, and then we squeeze them, and we do see that the hard layers continue to experience more tensile stress. So it's not like it's going to self-quench, right? So as the harder stuff, it quartz and the feldspar part of it's moving, and the biotites are sitting still, then this is a biotite squish, the quartz and the feldspar are going to stay in a more tensile state. Okay, so, oh my gosh, I'm back on ahead. All right, so here are my conclusions. So I would like for you to go away believing that stress percolation, which is known to occur in granular material, should occur in rocks just because we have anisotropic, elastic, and plastic properties on the single crystal scale. And that the patterns are a function of the variation in the elastic and plastic properties, and that basically all the components of the stress tensor can be seen as percolating, and that the strain can percolate as well. And basically, we should think of stress percolation patterns as like a foundation for everything else that happens. So it's kind of a mistake for my structural geology colleagues to say elasticity is not important because the strain is very small, right? It's very small. We don't get very much strain elastically when we deform a rock. It's plastic strain that makes the shape change. But it is the foundation for all of the mechanical and chemical processes that happen subsequently. So even though it's a small strain, it's important. So it impacts the bulk rheology, shear localization, perhaps phase separation, foliation formation, and sound speed and attenuation may also be impacted by the distribution of the stresses, as my friends demonstrated in their resonant ultrasound paper. So I think that's it.